First of all, introduce myself. Myself, Dr. R Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today, I am going to discuss about the topic is spectral studies on the chromium 3 plus ions doped in sodium lead borophosphate glasses. So, last and previous session was discussed on the EPR and optical observation studies of iron 3 plus doped borophosphate glasses. So, in previous section, we have discussed the introduction, experimental methods, techniques, results and discussion, and conclusion. These are we discussed in the last session. Today I am going to discuss about the spectral studies on chromium 3 plus ions doped in sodium lead borophosphate glasses. Outline of the today talk is introduction on the sodium lead borophosphate glasses, experimental methods and techniques for the sodium lead borophosphate glasses, results and discussion on chromium 3 plus ions doped in sodium lead borophosphate glasses. Finally, conclusions. These are we are going to discuss about the today topic. So first is general introduction. So glass is one of the most important material in modern information and communication and laser technologies. The drastically growing market for TV, television screens and data displays need glass with a variety of coating on its surface. Glass is extremely stable against environmental attacks. So glass is generally extremely stable against environmental attacks. Glasses are roughly speaking liquids that do not crystallize even at a very low temperature. Also, it do not crystallize at even low temperature. So that is one of the important unique property for glasses. So glasses are very versatile material due to the fact that they can be easily doped with transition metal ions as well as rare earth ions. So we can dope with a glass material. We can use the transition metal ions, that is chromium 3 plus ions, Mn2 plus ions, iron 3 plus ions. These are transition metal ions. In the same way, rare earth ions, samarium 3 plus, dysprosium 3 plus, erbium 3 plus. These are some example of the rare earth ions. Whenever doped into the glass materials, it can exhibit a different kind of spectral properties. Next is the introduction for the spectral studies of chromium 3 plus ions doped in sodium lead borophosphate glasses. So first introduction, we have to see the chromium ions with 3D3 configuration are of interest for solid laser materials. These are the chromium 3 plus ion mainly belongs to the electronic configuration D black elements. So 3D3 configuration. This is the electronic configuration is outermost electron orbital is 3D3 configuration. So these are the more interest in the solid state laser materials due to their ability to generate laser emission in the near infrared spectral region between 1.2 and 1.7 micrometer. So we can use between the spectral region from 1.2 micrometer to 1.7 micrometer. We can get the different kind of laser emissions in the near infrared spectral regions. So in recent years, renowned studies on optical performance of chromium 3 plus ions in crystals and glasses have been reported because of the explanation of these materials as active media for infrared tunable lasers and to aid to fundamental understanding of the interaction between the impurity and host lattice. This mainly belongs to the interaction between the host material. That means here host material is borophosphate and the impurity means that is the chromium 3 plus ions. This interaction we are going to study this is one of the fundamental understanding study involved in the sodium lead borophosphate glasses. So among the glasses, phosphate glasses have been of large interest for the variety of technological applications. So in borophosphate glasses, mainly in the phosphate glasses, it gives the more variety of technological applications due to the several unique properties such as high thermal expansion coefficients. So phosphate glasses having the high thermal expansion coefficient, low viscosity, low chemical durability. So these are the important property in the phosphate glasses. It exhibit the high thermal expansion coefficient as well as low viscosity, low chemical durability, UV transmission or electrical conduction. This also exhibit in the phosphate glasses. The addition of boron oxide improves the high chemical durability of borophosphate glasses. So this is the addition of whenever adding the boron oxide into the phosphate glasses, it can improve the high chemical durability of borophosphate glasses. So these are the important properties in the sodium lead borophosphate glasses. Next, coming to the material selection. In the present study, we are what kind of material we are used to prepare the chromium 3 plus ions of sodium lead borophosphate. So material selection. How to choose the material selection? So first, the present section highlights the facts, advantages behind the selection of boreal glass systems for the present study. So in spectral studies and in the present study, they focused on the mainly spectral studies on chromium 3 plus ions doped sodium lead borophosphate. We can say simply sodium, sodium lead Pb borophosphate glasses. So, doped with chromium 3 plus ions. This is the main composition of the present study. That is the chromium 3 plus dope sodium lead borophosphate glasses Bp, NaPb, Bp, doped with chromium 3 plus ions. So in our study, the main chemical composition of the chromium 3 plus doped sodium lead borophosphate glass system is shown below. This is we are taking sodium phosphate, NaPO3 by 6. This is sodium phosphate. Next, lead oxide PbO and boron trioxide B2O3 40% and Cr2 chromium trioxide Cr2O3. These are the we are selected chemical composition of the present study. First one is 30 minus X of sodium phosphate, 30 of lead oxide, 30 mole percentage. Next remaining 40% of boron trioxide. Next remaining X mole percentage of chromium trioxide. Here X varying from the different concentration of the chromium 3 plus ions. See here from starting from 0.5 mole, 2 mole, 3 mole, 4 mole and 5 mole. These are the we are varying the concentration dependence on the host materials. We are choosing the host material is borophosphate. We are adding the glass modifiers is sodium and lead, PbO and lead oxide. So this is the we are choosing the chemical composition of the present studied glass. Next, coming to the experimental technique, preparation of the glass material. So this preparation of the glass materials by using the melt quenching techniques. This is the one of the unique technique to prepare the glass materials. In our case, in our present study, we are using glass composition is sodium lead borophosphate. Previously, so the above chemicals, sodium phosphate, lead oxide, borate, chromium trioxide. These chemicals we can weighing to the by using of optical balance the weight of grams from 8 to 25 grams of weight we have taken into the preparation purpose. So we are after taking the chemical composition, we can pour into the platinum crucible. We can keep the weighed materials or chemicals into the platinum crucible. Then that platinum crucible kept in a electrical furnace. That is the electrical furnace at the melting temperature at 950 degrees centigrade. Melt duration is 30 minutes. So this is the in that way we are going to prepare the glass sample. This is a melt quenching technique means we can use the high temperature from we are using melting temperature here in the case of borophosphate glasses we are using temperature is melting temperature is at 950 degrees centigrade. So suddenly we have to cool down to the room temperature. At that time glass will be formed or glass will be fabricated. So in this way, we are going to prepare the glassy sample. After melting of the glass material, we can quench the at room temperature and pour into the preheated brass mold at the temperature of 300 degrees centigrade. This is the annealing temperature at 300 degrees centigrade. This how we are choosing the annealing temperature means we have to know the below the glass transition temperature of the borophosphate glasses. Below the glass transition temperature, we can use the annealing temperature at 300 degrees centigrade. So why we are using for the annealing is it to avoid the thermal stress and strain and give the more stability of the glassy sample. That purpose we are doing the annealing at 300 degrees centigrade. After annealing the temperature of 300 to room temperature, we have to keep in the annealing for 10 hours or 12 hours. After that, reach to the room temperature, we can take into the sample and to cut the different kind of required pieces, and we can polish the glassy sample, and we can send for the different kind of optical and structural measurements. So first we have to measure the XRD profile. Since we need to know the this is a prepared glass sample is glassy nature or crystalline nature. So whenever if you study the XRD profile, we can know the if you are getting the broad peaks, each and every peaks will be broady peaks we can get, that is known as a glassy sample. Whenever you are getting sharp peaks, that is mainly belongs to the crystalline nature. So in our present study shows the all the peaks are shown in the broad curves. So that is why you can say as a the present study glasses completely shows the glassy nature. So in that way we can measure the XRD studies. So in XRD only we can know the crystalline nature or glassy nature. Finally we conclude that this prepared sample is completely glassy nature. Next, coming to the experimental technique or methods of the characterization of the our prepared glass sample. First we need to measure the EPR spectra. First study is the EPR, that means electron paramagnetic resonance study. See, in this study we can use the electron paramagnetic resonance EPR spectra at sample were taken on a dual Fe1x ESR spectrometer operating in a X-band frequency. That is, the frequency is we are using microwave frequency 8.8 to 9.6 gigahertz for the EPR spectra with a field modulation of 100 kilohertz. These are the EPR spectra we are using. This is purchased by the Japan company one. This is GL FE1X ESR spectrometer of the X-band frequency. So there are different kind of bands is there, X-band, W band, Q band. So in our present study we are using the X-band. That frequency is around 8.8 to 9.6 gigahertz. That means microwave frequency we are fixing the that microwave frequency. Then we are varying the magnetic field in gas that we are varying, and you have to study the EPR analysis. So second one is absorption spectra. From absorption spectra analysis, we can use the Perkin-Elmer spectrometer. That company name is Lambda 950 in the wavelength range of 250 nanometer to 2500 nanometer. So optical absorption spectra, we are measure the absorption samples in the wavelength range of 250 to 2500 nanometers. Next, last one is fluorescence spectra, that means emission spectra. So in emission spectra, we are using Jobin and Fluorolog 3 spectrophlorimeter using xenon arc lamp as a radiation source. So this xenon arc lamp we are using for pumping source. Radiation source is a for pumping purpose. We have to excite the sample, then only it give the emission peaks. So that is why we are using the xenon arc lamp as a radiation source. That is pumping purpose. We are using for the xenon arc lamp. That is excitation, and it gives the fluorescence spectra. So these are the calibration techniques for the present chromium triple science doped sodium lead borophosphate glasses. So after a calibration technique, we can measure the first EPR spectra at room temperature as well as different low temperatures. So first figure shows the EPR spectra of chromium 3 plus doped sodium lead borophosphate glasses at room temperature. So we have studied the different concentration of chromium 3 plus ions starting from 0.5 mole percent, 2 mole, 3 mole, 4 mole, 5 mole. These are the different impurity concentration, that is chromium 3 plus ion concentration at room temperature. We are studying the EPR spectra. In this spectra, we are getting two peaks. One is at G equal, this G means Landé spectroscopic factor, that is 1.97 resonance peak. Next, other one is G equal to 4.55. So in this at room temperature in EPR spectra, we are observing two resonance peaks. One at G equal to 1.97, other one is G equal to 4.55. These are the resonance peaks observed in the room temperature EPR spectra whenever varying the chromium concentration from 0.5 mole percent to 5 mole percent. This figure 2 shows the EPR spectra of the 3 mole chromium dioxide doped with a sample, that is we are studying the various low temperatures from room temperature 295 Kelvin to at room temperature at low temperature 123 Kelvin. So we are studying the different low temperatures. In this low temperature, we are using the liquid nitrogen. liquid nitrogen we are using for the low temperature measurements purpose. We are using liquid nitrogen. Then only we can vary the temperature from room temperature to at low temperature of 123 Kelvin. So these are the low temperature EPR spectra. So here also we are getting the two resonance peaks, same as at room temperature. G equal 1.97 here. Other one is G equal 4.5. So first we have to discuss about the room temperature EPR spectra. So EPR spectra at room temperature is EPR spectra of all the investigated sample exhibit two resonance signals at room temperature as shown in figure 1. The EPR spectra exhibit weak and low field resonance signal. That means here weak and low field resonance signal we are getting G equal. That means low field. That means because we are varying the magnetic field versus first derivative absorption curve. So weak field we are getting G equal 4.55 resonance signal and high magnetic field G equal 1.97 you are observing. So here that is the EPR spectra exhibit weak and low field resonance signal with effective G value equal G equal 4.55 and a strong and high field resonance signal at G equal 1.97. So this what information we are getting from the this resonance signal means in this work the authors observed the resonance signal at G equal 4.5 and the other one is G equal 1.97. The resonance signal at G equal 4.5 is assigned to the isolated chromium triplet. This is mainly due to the whenever in EPR spectra, whenever doped with the chromium triplet science, we are getting the resonance signal at G equal 4.5. That is mainly due to the isolated chromium triplet ions. The intense resonance signal at G equal high magnetic field, that is G equal 1.97, may be due to the both exchange coupled chromium triplet ions and isolated chromium triplet ions. This is mainly due to the both exchange coupled of chromium triplet ions and isolated chromium. This is the interaction between chromium triplet ions to isolated chromium triplet ions. That means exchange couple means exchanging from one level to other level. That chromium triplet ions to isolated chromium triplet. These are the that interaction takes place. That is why you are getting resonance signal at G equal 1.97. These are the important resonance signals whenever you are observing in the study of chromium triplet ions doped in sodium lead borophosphate glasses. Next, coming to the EPR spectra at different low temperatures from high room temperature to 123 Kelvin. So here EPR spectra of sodium lead borophosphate glasses sample were also studied at various low temperatures from 123 to 295 Kelvin and the spectra are shown in figure 2. It is observed that the resonance signal intensity is decreased with increasing temperature. If you see here, we are temperature from at room temperature to low temperature. So this intensity will be at a low, high temperature intensity will be low. If decreasing the temperature, it will intensity of G equal 1.97. The resonance signal intensity will be increasing while decreasing the temperature. That intensity is increasing at resonance signal G equal 1.97. This is the one of the important phenomena in the Boltzmann distribution law. We can study whenever the decrease in the temperature, the resonance signal intensity will be increasing. So that we are studying here. So the resonance signal intensity decreases with increase in the temperature. So temperature is increases, the resonance intensity will be. So in the low temperature EPR analysis, the authors observed the resonance signals in the vicinity of G equal 4.55 and G equal 1.97. As shown in the figure 2, the resonance signal at G equal 4.5 is assigned to the isolated as is the same as the at room temperature what you discussed, same only we are assigned here. G equal 4.5 is assigned to the isolated chromium triplet ions. The intense resonance signal at G equal 1.97 may be due to the both exchange coupled of chromium triplet ions and isolated chromium triplet ions. These are the we are getting the two important resonance signal while measuring the room temperature EPS spectra at low temperature EPS spectra. Next, coming to the after measuring the EPS spectra analysis, we can calculate the number of spins participating in the resonance. That is N value. N value we can calculate it by using the EPS spectra analysis data. The number of spins participating in resonance can be calculated by comparing the area under the absorption curve with data of standard copper sulfate 5H2O in this study of known as concentration. So here we are using the sample and reference are standard sample. That is standard sample or reference is copper sulfate. Now our present study is chromium 3 plus ions. So we are using chromium 3 plus is the present study, that is X is the year AX, scan X is the AX, X means present study of chromium 3 plus ions. Next, A standard means area of the reference sample, copper sulfate sample. So here A is the area under the observation of sample as well as standard sample. Scan also same, sample and reference. Magnetic field corresponding to unit length of the chart. Next, G is the gain, BM is the modulation field width, P is the power of the microwave frequency. That means we are using the microwave frequency. That is frequency F equal we are using 9.6 gigahertz. That is a microwave frequency is fixed. So that at that time how much power you are using, that is power of microwave source. So these are parameter we can use to calculate the number of spins participating in the resonance signal. From EPR data we can calculate the number of spins participating in the resonance. N value we can calculate by using this formula. This is the important formula to calculate the number of spins participating in resonance. This same EPR data only we can analyze the a flat of log n versus 1 by t. At the same time we can study the variation of paramagnetic susceptibility with different temperatures. So first figure shows the 1 by t versus log n. So here number of spins oscillations in the resonance signal we can calculate it by using this formula. We are calculating the number of spins participating in resonance. That value log n versus 1 by t we are draw the graph. So after fitting the data points in a linear fit, we can get the data is log n equal to 18.70 plus 62.39 by t. By using this linear fit value, we can calculate the activation energy of the present chromium 3 plus ion doped sodium lead borophosphates. In the present study, we are getting the activation energy equal to 2.87 into 10 power minus 21 joules or 0.012 electron volt. We are getting by using the number of spins participating in the resonance signal. By using that data, we can calculate the activation energy of the present glass sample. Next, in second figure shows the temperature versus 1 by psi susceptibility. The reciprocal of the susceptibility, that is 1 by psi versus temperature. So this means we are low temperature data we are studying. In that data, we can fit with the linear fit by using the 1 by x equal to 6.03 plus 0.063 by T temperature. So by using this data, we can calculate the susceptibility by using the formula psi equal to n g square beta square j into j plus 1 by 3 into kb into t. Here n equal number of spins participating in the resonance, g equal to Landau splitting factor, b is Bohr magneton, j is the quantum number, next orbital quantum number, kb is the Boltzmann constant, t is observed. By using this formula, we can calculate the susceptibility of the paramagnetic ion of the chromium 3 plus ions. Same using this formula, we can by using of Curie-Weiss law. So temperature, that is Curie-Weiss law tells the susceptibility equal to C by T into theta P. That means C is the here, psi is the susceptibility, C is the Curie constant, T is the observed temperature, theta P is the Curie temperature. So by using this formula as per the Curie-Weiss law, we can calculate the Curie constant and paramagnetic Curie temperature. In the present study of chromium 3 plus ion doped lead borophosphate glasses shows the Curie constant is 95.71 EMU per mole. Next, paramagnetic Curie temperature theta P equal 110 Kelvin. These are we are getting the chromium 3 plus ions doped in sodium lead borophosphate glass. So in this graph, we can study the activation energy as well as Curie constant and the paramagnetic Curie temperature. These values we are going to study by use of EPR data. Next, coming to the optical absorption spectra. In the present study, the figure 5 shows the optical absorption spectra of 0.5 mole percentage of sodium lead borophosphate glasses at room temperature. We can study the optical absorption spectra. So it can optical absorption spectra exit 4 bands. Important, it observes the from ground state to different excited states. That is absorptions from portrait T1GF and portrait T2GF and doublet T1G, next doublet EG of G. These are the four important optical absorption bands or excitation bands from ground state. So optical absorption spectra of sodium lead borophosphate glass of chromium doped ion glass sample in the wavelength range studied from wavelength range from 200 nanometer to 800 nanometer, that is shown in the figure 5. This spectrum exhibits four important bands centered at 447 nanometer. That is first peak we can get the 447 nanometer, that the energy of 22,370 centimeters. Other one is 632 nanometer, that the energy is 15,820 centimeters. Other absorption band shows the 653 nanometer, that the energy is 15,315 centimeter inverse. The last one is 687 nanometer, that is energy of 14,557 centimeter. Among these, the band at 447 is the most intense. Compared to this bands, this band is the more intense band at 447 nanometer. Because in optical absorption spectra or excitation spectra, we can which absorption band we get the more intense band. That band we can use for the emission purpose. We can use that wavelength for excitation source. So in our present study, we are intense band we are getting at 447 nanometer. So this band used to excite the emission spectra we can analyze by using source of the 447 nanometer of excitation band or absorption band. So we are studying here optical absorption spectra. In table 1, it shows the observed and calculated band positions along with their assignments for chromium 3 plus ions in sodium lead borophosphate glasses. By using this absorption data, we can calculate the crystal field parameters. So we are getting the four absorption bands from transition from ground state to different excited state. That is, ground state is portrait A2GF to different excited states. Portrait T1GF, portrait T2GF, next doublet T1GG and doublet EGG. These are the four bands of absorption bands from ground state to different excited states. These are the observed wavelengths and these are the energies. This calculated wave number by using the Tanabe-Savano diagram. We can calculate the different energies by using the Tanabe-Savano diagram. In that diagram by using, we can calculate the crystal field parameter DQ value and the Raka parameters, Raka inter-electronic repulsion parameters B and C also we can calculate by using the absorption data. So here the crystal parameter DQ is evaluated from the band position of the ground state from portrait 2GF to portrait 2G. So by using this second peak, we can get the DQ parameter we can calculated. The value of Raka inter-electronic repulsion parameter is evaluated using the relation given by the dq by b equal 15 into x minus 8 by x square minus 10x. Here x value how you can calculate the different energies of E1 and E2 minus dq. That means E1 means 447 nanometer, E2 energy is 632. This by using these two absorption wavelength we can use the x value. By using getting the x value we can substitute in the formula dq by b equal 15 into x minus b by x square minus 10x. By using this data we can calculate the b value. So that in this using this formula we can calculate the crystal field parameter as well as Raka inter-electronic repulsion parameters B and C. So in the present study we have calculated dq value. Crystal field parameter value is 1582 centimeter inverse and B value 662 centimeter inverse and C equal 3200 centimeter inverse. These are the Raka inter-electronic repulsion parameters. Next coming to the emission spectra. So in the emission spectra, figure 6 shows the emission spectra of the sodium lead borophosphate glasses at dopant of chromium ion concentration is 0.5 mole percentage. 0.5 mole percent of glass sample at room temperature. This is the emission spectra data. So we are scanning from 500 nanometer to 650 nanometers. We are observing we are exciting using is 448 nanometer because we are getting the intense band at observed spectra. We are getting 447 nanometer. So we are choosing that same wavelength as a excitation source to measure the emission spectra analysis. So in the emission spectra of sodium lead borophosphate glass excited at 448 nanometer as shown in figure 6, the emission spectra exhibit a broad band. This broad band is assigned to the quarter T2G F2, quarter A2G, that means excited state to ground state. So this emission around 720 nanometer, this deep red emission, we can observe the energy of 13,888 centimeter inverse, we can get the broad emission while doping the chromium 3 ions in sodium lead borophosphate glasses. This is the information from getting from the emission spectra analysis. Next, finally, conclusion or summary of the present study is EPR spectra of chromium 3 ions doped sodium lead borophosphate glasses exhibit two resonance signals with the effective wave G values at G equal 4.55 and G equal 1.97. These signals are attributed to the isolated chromium 3 ions and exchange coupled of chromium 3 pairs. Next, from the optical observation spectra exhibit four bands characteristics of chromium 3 ions nearly this shows the octahedral sites. From the position of the observation band maxima, the crystal field splitting parameter and Raka parameters B and C have been evaluated from using the optical observation analysis. From emission spectra, last one is the emission spectra exhibit a broad band expected for chromium 3 ions in the octahedral symmetry. In observation spectra and emission spectra, we can observe the chromium 3 ions shows the octahedral symmetry. The emission spectrum exhibit a broad band centered at 720 nanometer. That means 13,888 centimeter inverse is energy is exhibit the chromium 3 ions. These are the conclusion or summary of the spectral studies on chromium 3 ions dope in sodium lead borophosphate glasses. So these are the list of references used in the present study. These are the cited references. This is the sixth reference. So this is one of the important reference, is one of the my reference, N Kiran and Cr Kesavulu. So this is published in this work is Physica B in the year of 2011. These are the list of references cited in the present study. So thank you, to be continued in the next section. So next section we can study the different analysis of the different borophosphate glasses. Once again, thank you.
Like, share and subscribe. Hit the bell icon for more updates.